after a fun ZK VM, the next talk is by Ariel Gabizon, the chief scientist at Aztec network. He's been talking all about Hasse's theorem and some of the important underlying primitives of elliptic curves that are used in almost all blockchains today.
Thanks very much. Okay, thanks a lot for coming. Let me first address the question of why to talk about a basic math theorem at ZK Summit. If I have to make an argument for it, it would be that my hope is that, by opening a little the elliptic curve black box beyond just being a group with hard discrete log and bilinear pairing sometimes, we can get interesting results for snarks. So just two recent examples are this first work of a way to prove that like a Pedersen hash is correct without actually computing it in the circuit, but instead using this classic theorem about something called principal divisors. And another example that got a lot of attention in our sort of field is this work of the Starkware people of how to get FFT-like algorithms even when we don't have our beloved subgroup of order that is a power of 2. Right, what is Hasse's theorem? So say we have some elliptic curve over a field FP, and we ask the question, how many points are there on the curve over FP? And let's denote that number by capital N. So we know that n is at least 1, because we always have what's called the identity of the curve, or the point at infinity. And we know that n is at most 2p plus 1. Why? Because, right, every value we put in for x, there's going to be only at most 2 options for y. So Hasse's theorem tells us that this number n is going to be very close to p, actually. So if we denote the difference, a as the difference between p plus 1 and n, then this difference is actually going to be at most 2 times square root p. So this is very foundational for elliptic curve cryptography, because it tells us, say we want a curve of a certain size, say size roughly 2 to the m. So how do we get such a curve? Well, we can just pick any prime p with m bits and just take any elliptic curve over fp, and we're guaranteed it'll have size roughly 2 to the m. Of course, it's not sufficient for elliptic curve cryptography because we'll want a prime order group of this size, but it's foundational for it. So let me walk you through some of the parts of the proof of this theorem, and hopefully show you some interesting elliptic curve facts on the way. So the proof begins with some junior high algebra, in a sense. So again, we're denoting by A the difference between the field size plus 1 and the number of points on the curve over fp. And this polynomial is going to accompany us for the whole talk. This polynomial L, which is x squared minus ax plus p. So the coefficient of x is like the difference between the field and the curve size, inverted, and the constant coefficient is the field size. So engrave this polynomial in your mind. And I claim that it's enough to show that if the roots of this polynomial, this is just polynomial over the integers, not a finite field, it's enough to show that the roots of it are not real numbers. Why is that? Because so again, going back to junior high math, right? We compute the discriminant when we want the solutions of a quadratic, which is here going to be a squared minus 4p. So, right, when there's no real solutions, we know that this discriminant is negative. And that's exactly going to show us that the absolute value of a is smaller than 2 square root b. Cool. Right. So let's, as a sort of warm-up and something we'll use later, let's show that we want to show the roots aren't real. Let's show they're at least not integers. So let's write, we know L, we can write it as a product of linear forms over just the complex numbers. It has some roots. And we know that then the constant term is going to be the product of these roots, and a is going to be the sum of them, just by multiplying out these products. So since p is prime, then there's only going to be basically 2 options for omega 1 and omega 2. The first one is that they're going to be 1, right? P is prime, and they have to be factors of p. So the only options are that they'll be, like, for example, 1 and p. But if that's the case, then a, which is their sum, will be p plus 1. And since a is the difference between the field and the curve, it will mean that there's no points on the curve. But we know that there's always at least 1 point on the curve, the infinity point. So this can't happen. And similarly, you can rule out the second option, which is minus 1 minus p. So this tells you that the roots of L are not, or at least not integers. And we'll use that a bit later. So now the next thing, we're going to take a little detour. The next thing is going to be to show, right, we want to know what are the roots of L over the complex numbers. The next thing is going to be showing that a certain what's called endomorphism is a root of L. So we're going to need to talk about endomorphisms for a few minutes. So what are endomorphisms? So this is like a definition I read 10 times, and each time I would forget what's the definition of it. Like all the things with phisms in the end would just mix in my head. So the way I remember it, it's homomorphisms, which is easier to remember. It's just any map that respects the group law, but that sort of know the group they're working with is an elliptic curve. So what does that mean? It means, the map respects the group law, as we've probably seen many times. But the knowing that it's an elliptic curve, it means that also this map, we can, if we look at the coordinates of the elliptic curve point, we can represent this homomorphism by rational functions in the coordinates of the curve. Right, and this bar here is, we're looking at points, solutions on the curve, not just over FP, but over the closure, so over coordinates in FP squared, FP cubed, and so forth. And an important point is that we can think of these endomorphisms as a ring. So right, for that we need to define multiplication of two of these. And multiplication is naturally going to be composition. So like psi1 times psi2, what is that? That's going to be just psi1 composed inside with psi2, right? And just as a little exercise, if both of these are expressed as rational functions, then definitely when we compose them, they can still be expressed as rational functions. So let's use this little notation. We'll use it towards the end. End E is the endomorphisms of the curve. And it's a ring. It has addition and multiplication. Cool. So let's look at there's basically two examples of endomorphisms. The first one is just this scalar multiplication. So we take a point P, and for some integer, we output C times P. And basically the reason this is an endomorphism is, right, we have equations for doing doubling and addition on a curve. So using that, we can express C times P as some rational functions of the coordinates. So the second example is what's called the Frobenius endomorphism. So this is like when you're taking the point x, y, and mapping it to the point x to the p, y to the p, right? So first of all, we see clearly it satisfies the third condition, right? We're expressing it as rational functions by definition. So one thing that maybe is confusing in the first, you're like, wait, isn't this the identity map? Because x to the p is just x. So here it's crucial that like we're looking at points over the algebraic closure. So this isn't just the identity map, right? And an interesting thing is sort of looking at the curve over the closure, it'll allow us to finally get this bound on the number of points over fp, which is what we want. So let's do a little exercise to see that this is really an endomorphism. So basically the reason it is that we have this little formula also for, right, that a plus b to the p, even when the points are not in fp but in an extension, is a to the p plus b to the p. And so let's see, you know, for example, like one thing an endomorphism has to satisfy is if it maps a point on the curve to another point on the curve. So let's see that holds. So let's start with some point x, y on the curve. So it's on the curve, so it satisfies this thing. So if this is 0, then I take it to the p. It's also 0. And now, because of this, this linearity of this raising to the power p, I can basically shove all the p's inside. And when I shove them inside, when it's something that's actually an fp, like these coefficients a and b, then the p just disappears. So what does this give us? It gives us that if the point xy is on the curve, so also the point x to the p, y to the p is on the curve. Right. So here's I'm going to basically, right, in this overview, I'm going to use two, heavy artillery, two big sort of cannons that, their proof is a whole thing. But the first sort of, heavy artillery I'm using is this theorem or lemma that this endomorphism, this Frobenius endomorphism, is actually sort of a root of this polynomial. What does it mean for the endomorphism to be a root of the polynomial? It means that if now, right, we showed how to do multiplication as composition. So if we're going to look at now this endomorphism, like phi squared minus a times phi, right? A times phi is like do Frobenius and then do scalar multiplication by a plus p. So this is going to be the all zero map on the curve. This is going to map all the curve to the point at infinity. Or to see this more explicitly, it means that for any xy on the curve, even one with coordinates in some big extension of fp, if you look at this point, like xy raised to the p squared minus a times xpyp plus p times xy, this is going to be the identity point on the curve for any point, even over the closure. And just, I felt I should, mention snarks. So maybe something interesting for snark optimization. I mean, we usually look at curves for, over just a prime field, but if we'll ever look at ones over p squared or whatever, maybe a nice little bit is that, right, you want to get, say, p times your point. So you can actually get it by a times your point, right? Where a, the number of bits in a is just half of compared to p minus this x to the p squared y to the p squared. So this gives you some shortcut of getting p times xy. Okay, so we're almost there. So we've shown, we've seen that this endomorphism, this Frobenius endomorphism, is a root of L in some sense. But we want to show that an imaginary number is also a root of L. So we need some way to map these endomorphisms to complex numbers. And this is where this theory of what's called complex multiplication comes in. So what it gives us is there's going to be some isomorphism from this ring of endomorphisms to some subring of the complex numbers. This ring I call here Re. And the crucial point is that Re, it's a subring of complex numbers, but its intersection with the reals is only Z. So more specifically, R is going to be all the points that you can write as Z plus Z times D for some imaginary number D. And now I claim to you, so this, right, this T is going to map the Frobenius endomorphism to some complex number, to some number in Re. I claim to you that this number is also going to be a root of L. Why? Because the fact that T is an isomorphism, right? So it sort of commutes with addition and multiplication. So if you write it out, you see you can replace the T and L. You can commute them. And now, so you have T of L of phi. L of phi, we know it's just the zero map. And now, right, so T is an isomorphism, so it's going to, what is it going to map the zero map to? It's just going to map it to 0. So this number that is mapped from Frobenius, let's call it omega, it's going to be an actual root of L. So now, right, we want to claim that it's an imaginary number. Well, we've shown before in our warm-up that a root of L cannot be an integer. So it's an RE, it's not an integer. So the only, right, so it's not, it can't be real. There's no other real numbers in RE, so it must be an imaginary number. And we're done, right? This means that discriminant is negative, and we've got the Hasse bound. Yeah, so that's it. How much time do I have left? 5 minutes? Oh, okay. So basically that's it. I do have one little slide. I'll do a little rant of historical. So where did this theorem come from? That the endomorphisms are equivalent to some imaginary ring in the complex numbers. So it came from sort of the 19th century, where people were studying elliptic curves over complex numbers, not over finite fields like we do in cryptography. And then there's this really cool equivalence. Maybe you've seen that all elliptic curves over complex numbers, they're equivalent to toruses, or so basically the complex numbers modulo a lattice. And then the endomorphisms there correspond to complex numbers that preserve the lattice, that don't, if you multiply anything in the lattice, it stays in the lattice. And sort of what happened was, Hasse was trying to prove this, and people, Hasse and others, were like, okay, maybe this whole theory of complex multiplication, maybe it also actually works over fields of characteristic P, and turns out it does, and they worked hard to prove it. And so where does this polynomial L come from? Very, I'll say very roughly, it's related to what's called the Zeta function of the elliptic curve. So right, there's this whole Riemann hypothesis where you want to prove that the non-trivial roots of the Riemann Zeta function all have like real part half, right? And it's very hard question, so people were looking for, okay, maybe for other zeta functions, we can prove it, that the roots are there. And it turns out that, yeah, for a zeta function of an elliptic curve is much easier to work with. And then proving that, the same thing about the roots of a zeta function of elliptic curve, it exactly implies that the roots of these roots omega 1, omega 2 we were working with, they have like absolute value square root P, right? Which also, right, gives us this bound, because this A was the sum of them. So I used to prepare this book. The first book you've probably all heard of. The second book is, I also recommend to look into it. It has a lot of interesting anecdotes. Also just doing math in Europe during the sort of beginning of World War II or just before that. So a lot of interesting personal anecdotes. And thank you very much.
Hey, we got time for 1 or 2 questions, and then we got a break for lunch. But so I think a mic is coming around. If you have a question, please speak into the mic for the recording's sake. Thank you. And if folks could try not to leave in too large a number before the question is done, I think that would be helpful. But we'll wrap up in 5 minutes. So. That's it.
Okay. I'll speak out loud. Thank you for a wonderful talk, Ariel. It's of course very sad that we haven't started from this torus stuff of complex numbers from the very beginning. I love this torus is Tori guys, the Tori people. Actually, a serious question. All this endomorphism that you talk about and this frobenius endomorphism, actually from the security perspective, I wonder, can it happen that we discover so many endomorphisms, easily computable, that discrete log becomes easy in curves? Because like so many kind of relations that relate kind of seemingly unrelated points, and how did it happen that like everything becomes breakable if we find so many relations like this?
Yeah, I don't know. That's an interesting question. Yeah, I don't know. Yeah.
Endomorphism is vanishing on the elliptic curve and say it's trivial. I agree, but how can I imagine the extra closure of the elliptic curve? Like what points to add? Is there like an imagination? Because I can imagine the elliptic curve.
I don't. Yeah, I don't know. I don't know how to imagine it. Sorry, it's not a very satisfying. I don't know. Yeah. So since I come from the crypto side, I guess my knowledge beyond what the slides is not deep or for the question. Sorry. Yeah.
Does the other root of L have any significance? We found Frobenius, that was useful. That's one of the root, I suppose.
Yeah, that's
Yeah.
a complex combination.
Yeah.
If you have a complex root of a polynomial, it will be 2. You can complex conjugate it with other root. Right. Sure.
Yeah, so in the complex numbers, it's going to be the conjugate. Yeah, so I wonder what endomorphism the other root corresponds to. Yeah, that's an interesting question. I don't know. But which automorphism exactly? Right, so the question, yeah, the conjugate, which exactly automorphism is it going to correspond to? The what, sorry?
Yeah, the involution. So you have this automorphism that squares 2 minus 1. And every elliptic curve comes with it. And I guess it's the equivalent to complex conjugation when you do it over finite fields.
Okay. Yeah, no, I guess the question is not what the conjugation corresponds to, what, like this, the conjugate of Frobenius, what does it look like as an endomorphism?
Yeah, I was saying that it's simply Frobenius composed with this involution.
Right, but what does the involution look like on the curve, I guess? Like what mapping is it exactly? Oh, just xy to x minus y? Oh, okay, so you're saying the conjugate to Frobenius is maps xy to x to the p minus y to the p, maybe. Yeah, that makes sense. That makes sense. Yeah, probably it's that.
Awesome. I think it's time for, we're going to take a break for lunch.
Thanks a lot.